Alright guys, let's go ahead and start talking about solutions. Now, starting off, we're going to talk about solution formation. Now, the nature of the solute and solvent. We need to circle solute and solvent. Solute is what is being dissolved, and solvent is what is doing the dissolving. Now, an example of a solvent would be water. Water is the universal solvent. An example of a solute would be like sugar. So if we were making sugar water, the water would be the solvent, the sugar would be the solute. Okay. Now, the factors that determine the rate of the solution, okay, meaning how fast the solution is made, how fast we can dissolve the solute in the solvent. The first thing is to speed it up. If we stirred it or agitated it, we shake it. That would be one way that we could speed up the formation of the solution. And if particles are made smaller, so if we take bigger chunks of our sugar water, if we took the big chunks of sugar and broke them up into tiny smaller particles, then it would form that solution just a little bit more quicker. Now, and temperature also increases the formations of solutions. Okay, if we heat it up, obviously the sugar would dissolve faster in the water. Now, when we're making solutions, in order to dissolve, the solvent molecules must come in contact with the solute. They physically have to come in contact together. So when we're stirring it, when we're agitating it, it moves that fresh solvent, meaning solvent that has not touched any of the solute, and it moves that fresh solvent next to the solute. Okay, the solute touches the surface of the solvent, touches the surface of the solute, and we see that we have the formation of a solution. Remember that those smaller pieces, we said it would speed up the formation, and the reason why is that the pieces increase the amount of surface area of the solute, meaning there's more sides that can touch the solvent. Okay, more sides to the solute. Now, with temperature, we see that higher temperatures makes the molecules of the solvent move around faster. We talked about this in gases. We talked about the kinetic molecular theory. We said if they move faster, we heat it up, it moves faster. That means that if we do this with a solvent, then it moves faster and contact the solute harder and more often. So therefore, it speeds up the dissolving. Now, this usually increases the amount that can be dissolved, meaning we can put more sugar in our sugar water if we heat it up. An exception to that is gases, so let's go ahead and box this, star that, highlight that, because that's important. Okay, gases are the opposite. Now, when we're talking about how much, we're talking about our solution. Solubility is the maximum amount of substance that will dissolve at a specific temperature. Okay, and solubility, when we do graphs and charts on it, it's always grams of solute per 100 grams of solvent. So how much solute can we put in 100 grams of our solvent? Now, a saturated solution, it contains the maximum amount of solute dissolved, meaning it reached full solubility, and we cannot put any more of the solute into the solvent. Okay, we put all that it's supposed to have. Now, unsaturated, that type of solution, basically it hasn't gotten to the point where it's saturated. You could still add more sugar. So if we have our sugar water, we have a glass of water and we pour in sugar, but we only put a tiny little bit in it, well, it's an unsaturated solution. It doesn't have as much sugar as it can take. Now, supersaturated solutions are solutions that are holding on to more than it theoretically can, meaning we have put in more than a saturated solution. It's supersaturated. We've heated this up and we've put in more of our solute, so it's impossible to do this without heating, but we heat up the solvent, and then the solute we can add a bunch more, and this is what happens when you see seed crystals will make it come out. And basically what you see if you ever made like sugar candy, rock salt, something like that, you've heated up water, put a lot more water in, and then or put a lot more sugar in, and it was able to come out. Okay. Now moving on to liquids. Okay, we talked earlier. We were talking about solutions, and basically we used the example of sugar and water. Well, here with liquids, we can also dissolve a liquid in a liquid. Okay, now miscible means that two liquids can dissolve in each other. Okay, so we have two liquids, we pour them together, and they're able to dissolve in each other. An example of this would be water and antifreeze, or water and ethanol. Okay, partially miscible means slightly. It's not completely dissolved in one another, but we see that with like water and ether, they mix partially. And then immiscible means that they cannot become a solution, that cannot dissolve in each other. Oil and vinegar, an example of this is, think of Italian dressing. You can shake them up as much as you want, but eventually they're going to settle back out and they don't dissolve one another. Now, for solids and liquids, as the temperature goes up, the solubility usually goes up. And we talked about this with our sugar and our water. We talked about supersaturated. If we heat up the water, we can add more sugar. Okay? For gases in a liquid, as the temperature goes up, the solubility goes down. So when we're talking about gases in a liquid, you can think of a can of Coke, and you have carbonation in there, that's CO2. Well, if we heat up a can of Coke and open it, all that gas is going to escape. Okay, because as we heat up a liquid, the gas wants to go away. Okay, the carbon dioxide cannot stay dissolved in that solvent. Okay, it heats up, it goes away. Now, for gases in a liquid, as the pressure goes up, the solubility goes up. Okay, so taking our same example with Coke, when they put carbon dioxide into Coke, what they do is they do it under pressure. That's why when you get a bottle of Coke and you squeeze it, it's just has a lot of pressure to it. And right when you open it, the CO2 starts to come up and it decreases the pressure. That's the sound you hear when you open up a bottle of Coke. Now, for gases and liquids, we have a law for this. It's Henry's law, and it says that the solubility of a gas in a liquid is directly proportional to the pressure of the gas above the liquid. Obviously, we increase the pressure, we increase the solubility. We decrease the pressure, we decrease the solubility. Okay, and we're using our example of a bottle of Coke. Okay, here's our equation for it. It's S1 over P1 equals S2 over P2. Okay, we increase solubility by increasing the pressure. Okay, directly proportional. One thing we can circle in the definition is directly proportional. Now, concentration is the measure of the amount of the solute dissolved in a given quantity of the solvent. Okay, a concentrated solution has a large amount of the solute. A dilute solution has a very small amount of the solute. Okay, so concentrated, a lot of solute. Diluted, very small amount. Now, that is a qualitative description. Concentrated and dilute, we're saying that it's qualitative. We're giving a quality to it. But there is a way that we can express it quantitatively, meaning right out beside quantitatively, put numbers. And we do this with molarity. Okay, molarity, it's the most important thing we're going to deal with. We'll talk about it a lot. This is what your homework's going to be about. It's going to be about molarity. Now, what it means is it's the number of moles of solute in 1 liter of solution. So main thing to circle here, it's moles of solute in liters of solution. Okay, looking at an equation, it looks like this: molarity equals moles divided by liters. We say when we're looking at concentrations, we're talking about a 6 molar solution we see that we've done moles over liters. This would be a 6 molar solution, would be 6 moles over 1 liter of solution. Now let's do an example. It says, what is the molarity of a solution with, we see we have 2.0 moles of NaCl and 250 milliliters of the solution. So we would take this here. We know that our molarity, big M, equals moles, which we have 2.0, all divided by, we see that we have 250 milliliters, which we know we can't use milliliters, we have to use liters. So we go ahead and divide by 1,000, and we will get 0.25. Okay, and we go ahead and we divide this out, and we should get 8.0 molar, or big M, molar solution. Now, when we actually make solutions, what we actually do is we pour in a small amount of the solvent and then add the solute to dissolve it, and then we carefully fill to the final volume. And how we do this in a problem, and what we'd see in a problem is like our example we have here. It says how many moles of NaCl are needed to make 6 liters of a 0.75 molar NaCl solution. So on this, what we're going to have to do is take our regular, and what we've done here is it's right here. We've already worked it out algebraically, but I'll show it to you. We have molarity equals our moles divided by our liters. Okay, so to here it wants to know how many moles. So we solve for moles, multiplying both sides by liters, and cancel it out, and we got this equation right here. So all we have to do is we take our equation where we have molarity, which is 0.75, multiply it by our volume, which is 6.0 liters, and it will give us moles of right around 4.5 for our answer. Now, when we're looking at dilutions, basically we're taking something concentrated, we're adding water to it. Now, in a dilution, the number of moles of solute doesn't actually change. We don't change the moles. We don't change the moles of solute that's in there. We're just adding more solvent. Okay, the number of moles before equals the number of moles after, so we can get this equation right here, where we have M1V1, which is our starting concentration and volume, and M2V2 are our final concentrations of volume. And basically what we use is we use a stock solution. They're pre-made to know molarity, and all we do is we take a stock solution and we just dilute it down by adding in more of the solvent. Okay, this is kind of like our Charles law, or Boyle's law, where we had P1V1 equals P2V2. Same exact type of algebra that we would use, except here we're dealing with more molarity and volume. Now, when we get into percents of solutions, remember that a percent means part per 100. So percent by volume, our equation for it is going to be this: our volume of our solute divided by our volume of our solution, and all multiplied by 100, not 100%, but 100. Okay, it indicates the percent by volume. So here's our question. It says, what is the percent solution of 25 milliliters of, this would be methanol, is diluted in 150 milliliters of water? So all we're going to do is we're going to take, if they're in the same units, it works out fine. You can keep them in milliliters. If one's milliliters and one liters, then you got to change it and make the units match. So we have 25 over 150 for milliliters, our two volumes, multiplying all of that by 100, and we would get a percent solution of 16.67%. Now, what we use the most is the percent by mass. And the percent by mass basically means that we have the mass of the solute in grams, all divided by the volume of the solution in milliliters. Okay, we multiply that by 100 to get our percent. Okay, and this is our percent by mass. And in this problem, it says 4.8 grams of NaCl are dissolved in 82 milliliters of solution. What is the percent of the solution? So what we take is we just take our 4.8 grams, all divided by our 82 milliliters, multiplying that by 100, and we get a percent of 5.85%. Now, moving on to our next example. Our next example can be just a little bit harder. It's asking us how many grams of salt are there in 52 milliliters of a 6.3% solution. Okay, so it's asking us to find the mass of the solute. Mass of the salt would be the solute, and then the solution would be our solvent, usually probably water. But here it says that we have our salt, this is our percent, this is our volume. So we're solving for mass. Okay, so we have to do a little bit of algebra here. So we have our percent by mass. Okay, we have that percent, it equals our mass all divided by our volume times 100. So if we're solving for mass, first thing we have to do is divide both sides by 100. Which gets rid of that 100. And then to get mass by itself, we multiply by volume on both sides. And we would get this equation where we have mass equals the volume times our percent by mass divided by 100. Okay, so we go ahead and we take this equation and we'll plug in our numbers for it. Okay, we take our percent by mass, which is 6.3%. all divided by 100, and multiply all of it by 52 milliliters, and that will give us a mass of 3.276 grams. A little bit different algebra than what we've done lately, but still we can use algebra to figure out what we have, solving for the mass of the solute. Now, colligative properties, it depends on only the number of the dissolved particles, not what kind of particles that we have. It just depends on the number of dissolved particles. Okay? And when we're looking at it, we're going to look at vapor pressure first. Vapor pressure, remember we talked about it in last chapter. We said that vapor pressure, when we collected the gas over the water, water had a vapor pressure. We always calculated that. Now, when we're talking about in solutions, we have to change a little bit of things and understand what's going on. Okay, it says the bonds between molecules keep molecules from escaping. So the bond between what's in the solution keeps it from escaping. It keeps it from becoming vapor. Now, in a solution, some of the solvent, so in this case, we'll think of our salt water, okay, or our sugar water. The solvent, the water, is busy keeping the solute dissolved. It's busy keeping that sugar dissolved. And so what happens is it lowers the vapor pressure. So the water's so busy trying to keep the sugar dissolved that the vapor pressure lowers. It's too busy to become vapor because it's worried about dissolving the sugar. Now, what we see is that normally salts are going to be electrolytes, and electrolytes form ions when they are dissolved. Basically what it means is if we take, for example, we have NaCl. When it's dissolved, it's going to break up and ionize and become our sodium ion and our chlorine ion. And because there are two pieces, what happens is it's going to lower the vapor pressure even more. Okay, we're looking at just the pieces. We're looking at the number of particles, and so therefore the salts, when they become electrolytes, they ionize and they have more pieces in there. So what happens is more pieces equal a bigger effect, meaning it lowers the vapor pressure even more. Now, boiling point elevation. What happens, we see that in solutions, the vapor pressure determines the boiling point. Okay, we just looked at the more pieces, the lower the vapor pressure. So we're looking at our vapor pressure, and it determines our boiling point. So the lower the vapor pressure, the higher the boiling point. Okay, salt water, in this case, salt water will actually boil above 100 degrees Celsius. Now, just regular old plain water boils right at 100 degrees Celsius, but if we add some salt to it, because it has a lower vapor pressure, it'll have a higher boiling point. Now, the number of dissolved particles determines how much, okay, so meaning how much salt is in that boiling water will determine how high it goes, as well as the solvent itself. So depending like the water, or if we're dissolving it into something else like ethanol. So the solvent has something to do with it, and the number of particles has something to do with it as well. Okay, and they'll all affect that boiling point elevation, meaning raising the boiling point. Now, the freezing point depression, we're talking about taking our solutions and lowering that freezing point. Okay, it says that solids form when molecules make an orderly pattern, and the solute molecules break up. So we're talking about that salt or that sugar in that water. It breaks up that orderly pattern and doesn't let it happen as easily. And what happens is it makes that freezing point even lower. It's got to take out so much energy because the solute's not letting it get in line. It's not getting in that nice orderly pattern. So it has to take more energy out of the system. So salt water will freeze well below 0 degrees Celsius. And how much depends again on the number of the solute particles dissolved. So more salt in the water, obviously a lower freezing point. Less salt, a little higher freezing point. Now, we already talked about molarity. We're going to talk about molality right now. Okay, it's a newer unit for concentration. It's new to us. It's the second one we're learning. And it's represented by a lowercase m. Remember, molarity is a capital M. Molality is a lowercase m. Now, what it means is we have the moles of the solute divided by the kilograms of the solvent. Keyword here is kilograms. Okay, moles in kilograms. We got to make sure that our units are correct. Okay, so we look at our problem. It says, what is the molality of a solution with 9.3 moles of NaCl in 450 grams of water? Okay, so here are our moles. Here's our mass. Remember that our mass has to be in kilograms, so grams to kilograms, we divide by 1,000. Move that decimal place 3 times. We get 0.450 grams, or kilograms. Okay, so we take it in our equation, and we have our molality equals our moles, which is going to be 9.3, all divided by our 0.450 kilograms, and we will get a molality of 20.67 for our molality. Now, the reason why we have molality is because the size of the change in the boiling point is determined by molality. So we use it to find how much our boiling point is going to change. And we use this equation to do it. Guys, really just showing you this right here so that you know that this is why we do molality. It's not just another thing to be confusing, but it's trying to show you what we use it for. And we see that delta TB is the change in the boiling point, and KB is the constant determined by the solvent. M is our molality of the solution, and N is the number of pieces it falls into when it dissolves. Okay, so we can kind of use molality to determine how much the boiling point is going to be affected. We do the same thing with freezing point, and we use molality for it. Again, it kind of uses the same variables, but just wanted you to know why we have molality.